Hi, so what I thought would be fun would be to go over a part of an exam that I gave, which I believe to be the hardest theory exam ever given by anyone. So this is only going to be half of the test. So the test was true, false, and open, which is what this is, and a multiple choice section, which had 50 multiple choice questions. So the point of this one is that you have to answer true, false, or open. So we actually went into complexity theory, or at least a little bit into it. And there are some questions in here that we don't know, at least currently, the answer to any of these open questions. So we say true if the answer is definitely true, false if it's definitely false, and open otherwise. So let's get started. So the number of decidable languages is uncountable. This is false because decidable languages correspond to at least some Turing machines, and Turing machines as a whole represent a countable subset of all possible languages because each one of them solves one language. So this is definitely just countable, so it's not uncountable. The language, this big complicated thing is regular. That is true. We proved that on the channel pretty recently. It's probably the hardest question on this entire thing, and it's a really cool proof. It basically you just you keep track of what the current remainder is. You focus on the A part first, and then for each of the possible remainders, you transition over to the same state where you have a B cycle, and then from each one of those, you transition to the C cycle, and then the D cycle, and then you're done. So let's go into question 3 then. The language of all binary strings, where the length of W is a power of n, and n is a positive even integer. So by power of n, I mean like n to the k for any k. At least, let's just say 1, it doesn't really matter. So this turns out to be not context-free. And the main reason is that powers of really anything is not context-free. It's actually a little bit more complicated here, was because you have an even integer downstairs. So then you have to do essentially the 2 to the n proof, where n is any positive integer. And you can show that that's not context-free. Notice that we don't actually care about what the characters are, so it doesn't even really matter that the strings are binary strings here. It doesn't make a difference. We're only really focused on the length, and checking the length is not context-free. All right, NP not equal to P space. So remember, NP is the set of languages that are done in non-deterministic polynomial time. P space we haven't done on the channel yet, but it's deterministic polynomial space, and this one is open as of the recording of this video. Knowing my luck, it probably is proven in the next 5 minutes, but it's currently open as I record this video right now. All right, EQ-DFA is not P space complete. So P space complete is like NP complete, but for P space. And so EQ-DFA is not P space complete. That is true. So this is actually really, really, really hard to prove. So I would think it's the second hardest question I've ever given. And the idea is that you show that EQ-DFA is in NL, or at least the complement is in NL. So NL means non-deterministic logarithmic space. You use the result of the Immermann-Shelshenny theorem, which we prove in class, which is that NL equals co-NL, where co-NL is the complement of the original one. So that means that EQ-DFA, no complement, is in NL. And one thing that you can prove is that NL is not equal to P space. So that would mean if EQ-DFA were P space complete, then it would not be in NL, but it is. So the reason for this one is something called the space hierarchy theorem, which says that if you use any amount of space more, like if you run in a certain amount of space and then you use a little bit more, then you can recognize strictly more languages. So NL, which is log space, is not equal to P space. Well, you can say, well, this is non-deterministic log space, this is deterministic, but a result of Savage's theorem says that P space is equal to NP space, which says that the deterministic version is equal to the non-deterministic version. And there's something called the non-deterministic space hierarchy theorem, which also holds in the exact same way. Okay, so that one is true, which is actually pretty surprising. It's purely because we can show that it is in NL. All right, deterministic context-free languages are closed under reversal. That is false. And the reason for that is that you can design a language which looks like A plus, I should do it this way. Let's do it. A union B union C star. So anything can go before with W, C, W reversed. And so this, where each of the W right here, the W is in A, B star. And if you reverse this, so where you have the W, this part first, and then you have this stuff after, then that turns out to be deterministic context-free. The reason is that if you take any DCFL and concatenate it with a regular language, that will become a DCFL. But in this particular case, informally, so I wouldn't, well, we didn't go over the DCFL pumping lemma, but it turns out that this is not a DCFL purely because we don't know where the first part ends and the second part starts. So that's the reason why it's not a deterministic context-free language. So the reverse is DCFL, but the original is not DCFL. All right, let L be this set of strings, checking if it's not regular. So there's a dependence on the number of zeros and ones here. So this is not. Actually, no, it's true. It's true because it says it's not regular. I was thinking false because it's not regular. Yeah, it is not regular. So call an NFA epsilon free if it does not contain an epsilon transition anywhere. So let N be such an NFA, and basically what it says is the corresponding DFA that you make may sometimes require all 2 to the n possible states, and that turns out to be true. So I think I did an exercise on this or a homework something. The basic idea is that you look at something like a language I call L to the K, which is all W's such that W has a 0 in the kth to last position. I don't remember the exact example, but it's something along those lines. And you never needed an epsilon transition in that case. And then that'll show that you can use all 2 to the n states. Sigma star is NP complete. This is false. And it's actually very, very cool why it is not NP complete. It's not P space complete or whatever. So the reason is that if it were NP complete, let's say 3 sat reduces to sigma star, then by reductions, this means that the things that are in 3 sat will be in sigma star, and the things not in 3 sat will not be in sigma star by the reduction. Don't worry about the polytime reduction, but it doesn't matter here. But that doesn't work because the things that are not in 3 sat can't map to anything not in sigma star because there's nothing not in sigma star. So there's no possible reduction to sigma star. So it's false. Enumerable languages are closed under concatenation. Enumerable is just another word for recognizable. Actually, it's not another word. It's just an equivalent model, which we haven't done on the channel purely by my choice. But recognizable languages are closed under concatenation, so that's true. And that's pretty simple to show. You just break it up the string into all possible 2 pieces, and run the recognizer in parallel on both pieces and across all possible ways of splitting it up. Run them all in parallel, and then just accept if any one of the times both of the 2 parts accept. All right, so all DPDA, which is all DPDAs with their language being sigma star is in P. I think, yeah, that's true. So the reason is that so this was actually a kind of hard one. So it's related to the question of PDA. It doesn't matter if it's deterministic here. So PDA is a polytime solvable problem. So then what you do is you run the construction which converts the DPDA into the one for its complement. And so that takes polynomial time because you only add a constant times n number of new states and transitions. So it's definitely done in polynomial time. And that would provide an instance to PDA, which we know to be polynomially solvable. So although this is actually not that easy to show, but you can show that it's not it is in P. So sub LBA is all pairs of LBAs with one being a subset of the other. So kind of like sub TM or sub DFA or something. So, and it says it's in time 2 to the n, which means exponential time. So this is false. And the reason for this is that it's actually undecidable. So it's not in any amount of time. And the reason is that if you let M1 be sigma star, then effectively we can solve the all LBA problem. And all sub LBA is undecidable for similar reasons that all TM is undecidable or all CFG is undecidable. There's a lot of ways you can go there. So that one's false. If L is a language, then L star is infinite. This is false. And the example, prototypical example is empty set star, which is only the empty string. And so that's not infinite. That's pretty easy to see. The algorithm that we talked about in class to solve 3-sat, or sat, but in this case it has to be 3-sat, took 2 to the n, which is just try all possibilities and then evaluate each one of the possible assignments. That took that amount of time. Nevertheless, there's an algorithm that solves in strictly less than 2 to the n time. So let's say like 1.999, however many nines to the n time, which is not the same thing as 2 to little o of n, which is open. So this one's actually true. So the reasoning for that is that so pick any variable and set it to be true, just for the moment. Then what you can do is you can set that variable to be true every other place. So pick any variable that occurs at least once. So if it occurs once, then without loss of generality, we can just set it to true, or set whatever whether it's negated or whatnot to be true. Otherwise, it occurs in 2 places. So then what you do is you set the variable to be true, and then it's set to true in all other places, and that reduces the formula even further. There are other ways that you can go. So if the variable is true right now, then try and then recurse on the rest of the thing. Otherwise, if it's not satisfiable with it being set true, permanently set it to false. And then what you can do is any other variable in the same clause one of the other 2 has to be set to true. So pick one of them and then set it to true, recurse. And then otherwise, if the first one that's false, second one is true, if that's not satisfiable, both of them have to be false, and the third one has to be true, or set to true, whether it's negated or not. And so that actually gets us around, I think, 1.8 to the n time or something. So it's actually quite complicated to prove that that's the case. Let me know if you want to see a proof of that down in the comments down below. All right, so if the language is NP hard, then L can be undecidable. That is true. So the prototypical example of here is ATM. So you can produce, you can show a reduction to ATM, and that takes polynomial time, and ATM is undecidable. So that's pretty simple. Let P be a C++ program, and let P be a string representation of it. Then we're asking the language of all programs that compile without errors. And this statement is not actually true in the real world, but it's close enough. You can assume that the C++ compiler uses a CFG for parsing, then L is undecidable. Then what we're really asking is that can the context-free grammar make this program? And that's the ACFG problem, which is decidable. So this thing is false. So it is decidable because ACFG is decidable. Okay, so it's asking, do they understand how to formulate one question in terms of another one? If there's an NFA with n states with a constant number of input symbols, so constant means big O1, then there's an equivalent regular expression which is little o of n. I'd have to think about that. I think because it's a constant number of input symbols, this is true. And the reasoning is that if you rip a state out, wait. Actually, no, that's false. That was my mistake. It's false. Because if you have every single state, because it's an NFA, not because it's a DFA. If it was a DFA, I think this would be okay, but I'd have to think about it. With an NFA, it's false. The reasoning is that you can have every single state going into the state that you're repeating, and then from the state that you're ripping. So every state goes to the state that you're ripping, and the state that you rip goes back out to every other state. So then when you try to rip that state, and this applies to all states, then what happens is the regular expression that you get from the conversion is going to be quadratic in the number of states. So it's not even going to be big O of n, even though it's a constant number of input symbols. But the question really here is there is an equivalent regular expression. So it's not like it has to be done by the GNFA method, but it could really be done, it's just any regular expression for it. And I'm not exactly sure about that. I think I should have phrased this as the regular expression you get from the GNFA method is O of n, and that is false. Okay, so let PC be the set of all languages that have polynomial times certifiers, vertifiers, and then that's equal to NP. That's true. That's one of the definitions of NP that we've talked about before. Let N1 and N2 be two NFAs with a certain number of states. Then there's a DFA, so DFA here, with at most N1 times N2 states that has the language this. So this is false. And the reason is that if you let one of the two be sigma star and the other one have the language that required all 2 to the n states when you converted it from before, then the DFA will require exponentially many states compared to the original ones. Let M be a Turing machine that accepts an input W if and only if there is a DFA that accepts W, then L of M is in time N. That is false. So this is kind of a trick question. The reasoning is M here actually can be any Turing machine at all. Because this says for any input W, there's a DFA for it, but that's obviously true. You can make a DFA for exactly one string. It's just that it's a different DFA for each one of them. So there is a DFA that accepts W, so the DFA depends on W now. So it's not the same question here. So yeah. So that one is false, I think. Actually, wait, hold on. I think I misread my own question. It's been a while since I gave this test. That accepts an input W if and only if there is a DFA that accepts W's. So the DFA does have to depend on W, but for the Turing machine, it has to not accept it. If it does not accept it, then that does not mean, then that means that there's no DFA to accept W, which is false. So that's false for a different reason. Same conclusion, different reasoning. So so for all inputs W, if the Turing machine does not accept it, then that means that there's no DFA to accept that input W, which is false. You can always make a DFA for a particular string. So that's false for a different reason. All right, let B be the problem of deciding if the length of a shortest path, so this is the shortest path problem, is at most some number k. So that is polynomial time solvable. So B is in P because you can just run, say, breadth first search on it, and then keep track of the number of states that use the distance, the shortest path distance from the vertices as you visit them. So that's in P. Let C be the problem if given two set instances satisfiable. Then B reduces to C. So C, so C is equal to 2 sat. It's just another phrasing of 2 sat, and that is in P. So here, what you can do, it does reduce to it because both of them are in P here. So the reduction can actually just make the 2 sat instance automatically from the graph, and because you have a graph here, you can make a 2 sat instance from it. Does it polynomially reduce though? So if it doesn't have a shortest path, it is purely because both of them are in P. So the polynomial time reduction works here. Let P be a PDA on n states and a constant number of symbol under converting P to an equivalent CFG. So this is the PDA to CFG conversion. Then without simplification, G will have big O n to the 4th rules, and that's true. So if you actually run through the construction, if you have a constant number of input stack symbols, the 3rd type of rule will require at most n to the 4th times a constant number of rules to be made. And the other ones are less than n to the 4th. So it will be a constant times n to the 4th, at most. Let B the problem of checking if a graph has a cycle of length 3 or not, so finding a triangle in a graph. Then clique reduces to this thing. So this is an open problem. So because B is polynomially time solvable, because you can just enumerate all 3 choices of vertices and then just check if there's a triangle for each one of them. So it's polynomially time solvable, but clique we don't know to be polynomially time solvable. If it were, then this would be true. If P equals NP, then this would be true, but we don't know the answer of that. Consider the problem of deciding whether of a given Boolean formula in this CNF, so this is a conjunctive normal form, so this is for 3 sat instances, is satisfiable, but anytime the formula has a literal x, it does not have the literal x bar, then B is NP complete. That's open, or at least I think it's open. Yeah, it's open, because this is actually polynomially time solvable. Actually, wait. Because here, anytime that you give the literal x, but an x bar does not exist, then just set whatever this is, whether it's the negation or not, set it to whatever it is to be true. And then therefore, because it's in CNF, this CNF, then that means the formula you're given is always satisfiable. So there's no instance to, so it's not open. So the formula that you give is always satisfiable. There's never an unsatisfiable formula given for this problem. So B is actually not NP complete because everything that you give to it is satisfiable, assuming that it encodes a formula, but there is a way of dealing with that. So it is not NP complete, because if it were, then that means that things that are not instances being reduced to this problem would have to map to things that are not satisfiable here, but there's no formula that isn't satisfiable here. So that's good. If a language is unary, we saw that L might not be regular, but L star is always regular. That is true. We've done it on the channel. If A is the union of 2 languages where the one on the left side and the one of them on the right side is DCFL, then C is context-free. That is false. And the reasoning is that we can let A and B be sigma star, and let C be any non-context-free language, and then this equation will hold. A CFG is idiotic if, so it's the term I made up, if all rules are of the form A goes to WB, where, oh, okay, this is actually interesting. So I thought the answer would be true when I gave the test, or actually I'm not sure. But it's actually kind of a trick question in some sense. Oh, actually, never mind. I didn't see the second type here. So I did have the right thought in mind when I designed this. So if every rule is of the form, you have any string of terminals you want with one variable. So the regular grammar definition is one terminal in a variable. But here we have, you can have any number of terminals that you want. And we're asking if this type of CFG is regular. This is true. And the reasoning is if you have a bunch of terminals, so W1 up to WNB, then what we can convert it into is A goes to W1 X1, and then X1 makes W2 X2, etc., up to Xn makes WNB. So it's effectively like the Chomsky normal form conversion, but slightly done differently. And each one of these is in the structure of a regular grammar, so then the whole thing is a regular grammar. So that's pretty easy. So let me get rid of some of this so I have some room. So irregular grammar is extending if, in addition, it has the rule type where you have the terminal on the right side. Then the language of every extending one is regular, so this is false. So the reasoning is we can make a grammar of this form for 0 to the n, 1 to the n. And the way that it works is that we have S goes to 0A, and then A goes to S1, and then S has empty upstairs too. So this, because if I apply this rule, that means I have to go down to the A variable to make the 1 on the end, and then recursively go to S. And so then therefore, this has 0 to the n, 1 to the n, but it's in this form. So yeah, that's pretty easy to see. All right, so let's get rid of this so I can see the next question. So any non-trivial property of the languages of CFGs is undecidable due to Rice's theorem. This is false because Rice's theorem deals with Turing machine languages, not CFGs. Suppose ATM is decidable, then EQTM is decidable. This is true because, yeah, so you can actually wait a second. Okay, so this is false. Yeah, this is false. Yeah, because if it was the other direction, if EQTM were decidable, then we can show that ATM is decidable. But this is the other direction, so that we can show that ATM reduces to EQTM, and we can also show that ATM bar also reduces to EQTM. But the thing is that ATM is recognizable and EQTM isn't. So these problems aren't really the same in terms of that. So therefore, EQTM is still not decidable even if ATM were decidable, purely because that these two languages are not both ATM is recognizable, but EQTM is not recognizable. All right. So sub reg DCFL, so this is just another language that I made up. So M is a DFA, D is a DPDA, and L of M is a subset of L of D, then this thing is undecidable. That is false. A lot of false problems in a row. So the question is that if we have L of M being a subset of L of D, then that's equivalent to saying L of M intersection the complement of L of D is empty. That's just an equivalent way of saying the same thing. But DCFLs are closed under complement and under intersection with regular languages. So then we can just feed the corresponding DPDA for this into the EPDA or whatever decider for, EPDA decider. And so that is decidable. So this thing is false. The time hierarchy theorem implies that time of n is not equal to time n log n, and that is true. Because the time hierarchy theorem says that... Actually, no, it's false. I omitted something. So it is false. A lot of false problems. So it says that if f of n... So if f of n is little o at... so g of n divided by log n, then time of f of n, I'm just shortening it for space reasons, is not equal to time g of n. So if f of n is strictly less than g of n divided by log n, then they're not the same. But the time hierarchy theorem doesn't work here because this is saying if you divide log n on this side, then we're going to get n on both sides, and those grow at the same rate. So we need little o here. That's what the time hierarchy theorem says. So this one's false. If a language is recognizable and the complement is recognizable, then L can be decided with an LBA. This is false. So just pick any language that is not decided by an LBA, but it is decidable. So then it would be recognizable and its complement is recognizable. Because if a language L has this property, then it's decidable by definition. Well, we prove a theorem on it. But it's not necessarily that it could be done by an LBA. So it's just noting that there's a difference between LBAs and Turing machines. The complement of a CFL is decidable. Finally, a true answer. So all CFLs are decidable, and decidable languages are closed into complement. Suppose I have a CFG with a certain number of terminals and variables, such that for any rule, the rule has at most 10 things on the right-hand side. Now convert into a grammar in CNF without simplifying, then one can now precisely determine the number of rules in G. So let's see. So the first thing that we do is we add the one new rule at the start, so we know that one. For the second one, though, the problem is we don't know which variables are nullable. So we don't know where to assign the, we don't know where to copy the rules around. So because of type 2 and maybe some of the other ones, it is false here. Because we don't know where to put the epsilon, we don't know where the epsilon rules are. And we don't know how the variables relate to each other. So this one's false. 36, for any language L, picking the same string 3 times for each string in the language is equal to LLL, and this is false. And the counterexample is if L is equal to 0, 1, just the two strings, 0 and 1, then LLL has 8 strings in it, whereas this one over here has 2 strings in it, and so they can't be the same. We want to color graphs, so I just put obscure application with networks just to be funny. Given a graph, we can color each vertex with 1 of k colors. So this is basically just saying, if I have a graph, so like this, and let's just say that it is 2 colorable. So this graph, we're trying to figure out whether a graph is 2 colorable, which means that I can assign colors on each of the vertices such that if there's an edge between 2 vertices, then there's nothing in common. The 2 colors are not the same if there's an edge between them. And it's asking if this is NP complete, but the problem is that this is polynomially time solvable, so therefore we don't know whether or not this is NP complete. So this is an open question. It's polynomially time solvable because the color actually doesn't matter, so just pick one color for one vertex, then every one of its neighbors has to have the other color, and every one of their neighbors has to have the original color, and it has to go back and forth between the two. So now we're asking, is 3 color going to reduce to 4 color? And the answer is true there. And we can assume that 3 colors NP complete. So the proof for this one is if we have some graph G like this, then what we do is we attach a new vertex to every other vertex in the entire graph. And if this thing is 3 colorable, then this guy has to have a different color than all 3 of the colors being used here. So this has to have 4 colors. If this thing can't be done with 3 colors, then this whole thing can't be done with 4 colors, because let's just say this, if this has 4 colors, then this one has to be a different color than all of them. And so therefore it would need a 5th color. And so this polynomially reduces because the amount of work to add these edges is at most n squared, because I might need to add, well, actually it's at most n, even better. So this is polynomially reducible. I have a Turing machine model where the Turing machine can never write a different symbol over where W is, but it can write any symbol past where W is on the tape. In other words, the input W never changes. Then this is equivalent to the standard model, and yes, this is true. And the reasoning is that if I have W right here, then what I can do is add a marker right here, and then do all of the work over here, and leave all of this stuff alone. Leave Brittany alone. So do all the work on the right side, and is doing the simulation of the machine. If you hit the pound sign, then that means you try to move left at the left-hand end of the tape before, and then you just reject at that point. Otherwise, you just keep doing the work over here, so it does exactly the same thing as it did before. All right, so then the final question is that if the polynomial hierarchy collapses, then it equals P space. So this is, I think this is open. I'd have to think. Is this open? So, yeah, so here if it has finitely many levels, so this is open. So it could be that, let's just say it all collapses down to the 2nd level, which means that P, we have P here, and we have NP equal co-NP, let's just say, maybe it collapses to the 2nd level. Then it still could be that P space is separated from NP. So all of the other levels of the polynomial hierarchy are right here, but it still could be, because P space is unlimited. I think this is still open. Let me know if I'm wrong into the comments down below, but I think this is open, even if the pH actually collapses. Yeah, so and it might not be that it's NP equals co-NP, but it doesn't actually matter for this question. But yeah, so that's half of the test. The other half is true and false, which I may do if you want at some later point. So let me know down in the comments down below if I got any of these questions wrong. I think I got them all right, but let me know if I got any of them wrong. As always, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, thanks for watching, and I'll see you next time.